Hey, welcome to The Explainer. Today, we are going to break down exactly how to nail your Btec Applied Science practicals. We're talking specifically about all those key skills you'll need for Unit 3.
So you ever stare at a blank page and wonder, how on earth do I design a perfect experiment? Well, let's look at it a different way. Instead of this huge, scary task, think of it as a journey. Seriously, when you frame it like that, it breaks everything down into a really clear step-by-step process. And trust me, it's a process you can absolutely master.
So, we're going to follow a 5-stage path, which is pretty much exactly how professional scientists do it. We'll go from that first spark of an idea to planning it all out, doing the actual experiment, decoding the results, and then the final verdict. This is going to cover everything you need for the unit.
Okay, so first things first. Every single great investigation, I don't care if it's enzymes, electrical circuits, or plant growth, it always starts small. It doesn't start with some massive, complicated theory. Nope, it starts with one single question. And the magic word here? Testable. Once you have that solid, testable question, you've got the foundation to build your formal hypothesis.
And this is your hypothesis. Look, it's not just a random guess. It's a really sharp, precise prediction that basically becomes the roadmap for everything you do next. A great example? Increasing light intensity will increase the rate of photosynthesis in pondweed. See how clear that is? It links a cause, the light intensity, to an effect, the rate of photosynthesis. And the best part? You can actually walk into a lab and measure it.
All right, let's move on to the planning phase. This part is so important. Think of it like building a house. You need a solid blueprint, and that blueprint doesn't just make your life easier, it's what makes sure your results are actually reliable and, valid. So for your Btec assessment, your plan has to hit 4 key areas. You got to identify your variables, justify why you chose your equipment, do a proper risk assessment, and then write a method so clear that someone else could follow it like a recipe.
This picture of the pondweed experiment is a perfect example. The one thing you're deliberately changing is the light intensity, right? That's your independent variable. Then, the thing you measured to see the effect is the number of oxygen bubbles. That's your dependent variable. But here's the crucial bit. Everything else, and I mean everything, the water temperature, the CO2 level, has to stay exactly the same. Those are your control variables, and they are so important for a fair test.
Okay, listen up because this is a pro tip for getting top marks. You can't just list your equipment. You have to justify it. Why a 100 milliliter beaker and not a 50 milliliter one? Why that specific thermometer? For example, you'd say you're using a volumetric pipette instead of a measuring cylinder because it's way more precise, which means less error. Or you'd choose a digital pH meter over indicator paper because it gives you a number, a quantitative reading, which is vital for something like an enzyme practical. It's all about connecting your choice of tool to how accurate and reliable your results will be.
And of course, safety. This is absolutely non-negotiable. You have to do a thorough risk assessment. You look at the potential hazards, like the ones you see here, and you have to identify them, figure out the level of risk, and then write down exactly what you're going to do to control it. Things like wearing the right PPE or following COSH rules when you're handling chemicals. It's a must-do.
Okay, plan's done. Now for the fun part. It's time to get hands-on. This is where you follow your method to the letter and collect that all-important raw data. This is the evidence your whole conclusion will be built on.
Now this is what a professional raw data table looks like. Getting this right is step 1 of good data handling. Just look at the details. You've got clear column headings. The units are in the headings only, not next to every single number. And you've got separate columns for your repeats. Getting organized like this isn't just about being neat. It actually stops you from making silly mistakes and makes the analysis part, well, a whole lot easier.
So, you've got your table full of numbers. But raw data like that doesn't really tell you a story by itself, does it? We've got to process it, we've got to analyze it, to find the patterns and figure out what it all actually means.
So where do we start with decoding all this data? The very first thing you'll do is process those raw numbers into a nice summary table. So thinking back to our pondweed experiment, for each lamp distance, you'd calculate the mean, the average of those 3 trials you did. It seems like a simple step, but it's super powerful. It helps smooth out any random little blips in your readings and makes the real trend in your data pop out much more clearly.
All right, if you want to take your analysis to the next level, we need to talk about standard deviation. Just think of it as a number that tells you how consistent your results were. It calculates how spread out your data points are from the average.
So if you get a really small standard deviation, that means all your repeat readings were tightly clustered together. And that's brilliant. It basically screams, hey, my technique was precise and my results are super reliable.
Okay, this leads us to one of the most important questions in all of science. Let's say you're comparing two sets of results. Maybe it's an enzyme with an inhibitor versus without one. You calculate the average for both, and yeah, they're different. But is that difference actually meaningful? Is it a real effect from the inhibitor, or could it just be a fluke, just random chance? How do you know for sure? Well, to answer that, we need a really powerful statistical tool.
And that tool is the t-test. What a t-test does is it statistically compares the averages of two groups. It crunches the numbers and gives you something called a p-value. Now, in science, the magic number is usually 0.05. If your p-value is less than that, you can say with 95% confidence that the difference you saw is statistically significant. In plain English, it means it's almost certainly not just a random fluke. Nailing the t-test is a massive leap forward for your Btec analysis.
All right, we're on the home stretch. It's time to bring everything together. This final stage is where you give your final verdict and, just as important, where you take a hard look at your own work and evaluate it.
This right here is the payoff. Your conclusion has to link all the way back to the very beginning. You need to clearly state whether your evidence, your averages, what your standard deviation told you about reliability, maybe even what your t-test said about significance, whether all of that supports or rejects the hypothesis you started with. This is it. This is the moment you finally answer your original question.
But wait, we're not quite done. Great scientists are always critical of their own work. So to get those top grades, you have to evaluate your method. What were the limitations? For instance, with the pondweed, counting bubbles isn't perfect, right? Because the bubbles can be different sizes. So how could you improve it? Well, you could suggest collecting the gas in a syringe to measure the volume instead. Finding those weaknesses and suggesting smart, practical improvements, that's what really makes an investigation stand out.
And there you have it, the complete investigator's journey. But in science, you're never really finished, because the very best investigations, they don't just give you an answer. They make you think of brand new questions to ask